before we kick off the actual presentation by John DeGose, let me just briefly get through some admin stuff. So the drinks and foods obviously provided, just come to me if you feel like there's not enough water or enough food. I'll try to sort it out. Bathrooms are in the very back, just go that way and then turn right. So that's that. Other thing I wanted to say, this is the Wi-Fi the leaflets with Wi-Fi passwords left on the tables, so help yourselves and feel free to use the guest Wi-Fi. And one last thing before we start, I wanted to say that Avast are hiring. We're looking specifically for, in this particular group, we're looking for people with interest into functional programming. And I want to emphasize that all levels are welcome, so you do not need to be an expert on FP. Just what's enough is interest, and we can sort of guarantee that there is enough of help and background provided in Avast in terms of functional programming. So there is quite a large community in Avast for using FP in real life projects. So go check out our careers campaign. There are leaflets on the tables as well, so go check it out if you're interested. Okay, so that's that. Are there any questions right now? So if there are no questions, then let me just briefly introduce our main and the only speaker for tonight. So today we are pleased to have John DeGose from the United States. He is a renowned authority in the space of functional programming. John is, versatile developer, architect, CTO, and entrepreneur. But most importantly, he's a major contributor to several open source projects, and he takes lead on some of them. Today, specifically, we'll talk about his project, ZIO, and how that's helpful in terms of handling side effects. So thanks again, John, for coming. And without further ado, let me welcome John on stage.
Thank you for that introduction, and thank you all for coming to my talk tonight. I want to thank Avast for hosting, and I will say it is not many companies that are hiring for pure functional Scala developers and are willing to host speakers like myself, and they invited me to do a full day of training here, so I really want to thank you, Tomas, and everyone else who was involved, Jakob, in setting this up. It's been great to be here and spend time with a whole team of people excited about doing functional programming. And not only are they hiring, but they have catered breakfast and lunch every day, which is awesome. So tonight I'm going to be talking about functional effects. Functional effects are at the heart of some of the most exciting work being done inside the Scala ecosystem. Functional effect systems are changing the way Scala developers write modern applications. And even though I'm not going to have as much time as I would like tonight to go into why that's happening and some of the cool reasons you should be excited about functional effects in Scala, I am going to spend a bit of time introducing you to the core concept of what a functional effect is. It can be confusing, especially the first time you see it. So I'm going to demystify functional effects, and I'm going to spend the rest of the evening talking about how do you compose different types of effects. And then finally I'm going to wrap up by showing you some of the drawbacks in one way of composing effects, introducing an alternative that's implemented in a library that I work on called ZIO, which offers a way to do async and concurrent programming in pure functional Scala. So today I will be introducing functional effects in the most general possible definition of the term. Outside of libraries like ZIO and Cat's effect and so forth, I'm going to talk about what a functional effect is at its essence, at its core. Then I'm going to take you on a tour of different types of effects, some of which you won't even recognize as effects, but if you step back and take a look at the big picture, you'll be able to see that, yes, all these are really examples of a much more general pattern. Then I'll talk about vertical effect composition. So when we have different types of effects, how can we combine them to get something that has their composition of effects? And there's one particularly popular way of doing that that originated in Haskell that is known as monad transformers. And monad transformers work reasonably well in Haskell, even though they're not perfect. They work less well in Scala. And tonight I'll be talking about some of the reasons why that is. After talking about monad transformers, I'm going to transition to talking about an alternate technique called effect rotation that is able to preserve many of the key capabilities of monad transformers, but in a way that feels a little more like idiomatic Scala and doesn't have the drawbacks of monad transformers. And then finally, I'm going to show you how you can see a real-world example of effect rotation in the ZO library that I work on. Introduction to functional effects. One of the most amazing things about functional programming is that it takes all the different concepts that we work with in programming and it turns them into a first-class value. Values are extraordinary things. Programming languages are designed to help you be very proficient at manipulating, transforming, and refactoring values. We have functions which allow us to remove duplication across multiple expressions. So if you see duplication across an expression, you can create a function that allows you to remove that duplication. We have variables, so if you see duplication inside of a single expression, you can extract a variable, and you can refer to that variable multiple times. And then we have combinators, which are ways of extracting out duplication across chains, workflows of common operations. And then finally, we have the ability to test values for equality and similarity and inequality. And all of these powers collectively make for a very compelling package. Give a developer a chunk of code that produces and manipulates value, and they know how to deal with that. Unfortunately, in the world of programming, there are lots of things that aren't values. There are types, which are not values. They have their own syntax, they have their own rules. You can't treat them as values except in independently typed programming languages, which are not production grade. There are packages, which again are things which are not first-class values. There are cases, for example, cases of an enumeration, or terms in a sum type, which are not first-class values. There are methods, which aren't values at all, even though Scala can, in some cases, convert them into a value, a function. There's input-output. So like a statement, an effectful side-effecting statement, that's not a value. And because it's not a value, you can't do things like storing it in a data structure, or returning it from a function, or accepting it from a function, or accepting a side effect from a function and returning a different side effect. Those are things that you can only do with values. You can't do them with side effects. And fields. So for example, if you create a case class with 2 fields in it, those fields are not first-class values. The best part about functional programming is it takes all those things, or at least as many of them as possible, and it turns them into first-class values. And as first-class values, you can take these things, you can pass them around. You can store them in data structures. You can accept and return them. You can define combinators on them that are capable of adding functionality to these values. In the case of effects, every effect can be thought of as doing something. If we want to turn that into a value, then instead of doing something, we're going to turn that into a description of doing something. So instead of going running, for example, if we want to turn that into a value, then we'll have a piece of paper that says go running on. Only in Scala, we don't actually write it on a piece of paper. We end up building a data structure that describes the act of going running. I'll give you a very simple example of a little program here that has effects in it. It's actually doing stuff. And this is not a value right now. This is a side-effecting procedure. It's a method called monitor, and what it does is it checks to see if a sensor was tripped. And if it was tripped, it calls the security company returning true. Otherwise, if the sensor was not tripped, it returns false. Now this is a piece of side-effecting code. The simplest possible way for us to transform this into a value is to build a mini language. We will build a data structure, that's that sheet of paper, that allows us to describe these operations. You can do that more or less by rote. In this case, I'm going to call this data structure an alarm. And this alarm is going to be a sealed trait, so it's going to be an enumeration, a sum type, and it's going to have 3 different instructions in it. It's going to have a return instruction, which returns a value. It's going to have a check tripped instruction, which allows us to look and see if the alarm has been tripped, if the sensor has been tripped, and to choose to return different alarms in the case that it's tripped or not tripped. And finally, it's going to have a call function, or a call instruction, that allows us to describe the act of calling the security company, as well as whatever we want to do after we call the security company. Now, using this extraordinarily simple, immutable data structure, we can create a model of the side-effecting program that you saw before. And it's quite simple. The type of our value will be alarm of Boolean. This is an ordinary immutable value. And what we do is we use the check tripped operation as the first operation in our program. And we pass it a function that will be passed a Boolean value, whether or not the sensor was tripped. And if it was tripped, we're going to return another alarm value, which is going to call the security company and then return true. And if the sensor was not tripped, we're just going to immediately return false. We've created a declarative description of the preceding side-effecting program. There are no side effects here. Everything is a data structure. And in fact, it's an immutable data structure. Now, this value is useful as an intermediate form in our program because now we can store it in data structures, we can accept it in our functions, we can return it from our functions, we can build combinators that act on values of this type. However, it's not going to actually interact with the real world. To interact with the real world, we need to interpret this data structure into the side effects that it represents. And this is called execution or interpretation. To do this in the case of the alarm data structure, we simply match against the 3 different cases, and if it's return, we return that value. If it's check tripped, we do what we did before. We check to see if the sensor is tripped. We feed that result into F, and then we interpret the result of calling that. And then finally, for call next, we call the security company, and then we interpret the remainder of the program. This interpret function, it's not a pure function. It takes this immutable data structure and it interprets it into the side effects that it describes, allowing us to regain the sort of real-world practicality of the preceding program without sacrificing the fact that now we can use this data structure in most places in our program. So this is a typical example of what a functional effect is, but in general, what a functional effect is some sort of immutable data type that is equipped with a set of core operations. And together, the data type plus these operations provide a complete type-safe model of some domain concern. Every single functional effect out there satisfies that definition. They look quite different. Not all of them look like alarm. I specifically chose alarm because you've never seen anything like it before and probably never will again. It's not very realistic, but it is an example of a functional effect because we had our data type, it was immutable, it had 3 different operations in it, and together we were able to create a complete model of the preceding side-effecting code. For every concern out there, there already exists, or you can create a functional effect to describe that domain. And I'll give you some common examples. If your concern is optionality, that is, you want to compute, and sometimes you're going to try to compute something, but it's not going to be there, then you can use the effect called option, which is built into Scala. It is a functional effect. It's an immutable data type, and it has a set of instructions, operations that allow us to build up programs that use the feature of that functional effect, which is optionality. And like all functional effects, we execute it. And at the end of the day, when we execute it, we get back either nothing if it wasn't there, or we get back the A that was in the option. Disjunction is another concern. So in some class of computation, we'll either produce one result or a different type of result entirely. An example would be errorful computation. So computation that can fail with some specific error, that's an example of our needing the effect of disjunction. We're either going to fail with something on the left, or we're going to succeed with something on the right. And this functional effect is also built into Scala using the either data type. And when we execute it, we either get back a left of an A, or we get back a right of a B. Non-determinism, less frequently used, but still used to do, for example, search, to solve problems in search, where we're looking for solutions satisfying particular requirements. There is the list data type. Of course, we use the list data type just for ordinarily storing data, but we can also use it as a functional effect that allows us to explore possible solutions to a given problem, and to filter those by one satisfying a given set of conditions. And when we execute or interpret that effect, we'll either get back a solution, maybe our top ranked solution, or no solution at all if no solutions were found, which corresponds to calling head option on a list. And then also another example of a functional effect not baked into Scala, but also extremely important, is the effect of input-output. So when our programs interact with the external world, that functional effect is described by I/O-like data types. So cat's I/O, Monix task, Zio's Zio data type, and so forth. Scala Z7's task type. All these allow us to describe input-output effects between our program and the external surrounding environment. And when we execute them, which is not a functional operation, we either get back some exception if some code failed, or we get back the A value that they succeed with. So I'm going to give you an example of a single fully worked example of a functional effect. And this is the effect of optionality, but it's in a way you've never seen before. You know what the option data type looks like in Scala. It has either some or none, right? It's a simplification of the real deal that we're going to look at now. The real deal is a full model of the functional effect of optionality. I'll talk about the relationship with option at the end. So I'll call this data type maybe. This is going to be a functional effect for optionality. So if we're concerned about things that may or may not be there, this is the functional effect we want to use. A maybe of A can succeed with values of type A. However, it can also fail to produce any value of type A. We're going to need 4 different operations to completely describe this functional effect. One operation, which I'll call present, allows us to take an A and to stick it inside a maybe of A. This is when we have something and we want to stick it inside the functional effect to represent the fact that it's there. Absent, on the other hand, is when we don't have anything, but we need to create a maybe that has some type. We're going to use that operation when we don't have it, and we want to indicate that. We want to indicate we don't have a value of that type, so we use the absent operation. The map operation is when we have a maybe of A, and we also want to map that A into a B by supplying a function. So the pair of the maybe of A and the function A to B you provide the map operation those two things, and you get back a maybe of B. And then finally, the chain operation will be used when we have a maybe of A, and then based on that A, we want to produce another maybe of B for some type B, and we want to combine both the maybe of A together with that callback into a single maybe of B. In order to implement this functional effect, all we have to do is define a sealed trait with the 4 operations we know we need. The present operation simply stores the A. The absent operation doesn't store anything. The map stores the maybe and the mapper function. And then the chain operation stores the maybe and then the callback. Once we have defined these 4 operations, we can then define map and flat map on the maybe data type. Furthermore, we can define present and absent on the maybe companion object. We now have everything necessary to define an interpreter for the effect of optionality. This interpreter matches the maybe data type, and it has to handle each of the 4 cases. If it's present, first off, it's going to interpret it to some type Z. And the user who's interpreting this data type has to supply some function or some value called if absent, which will be returned in the event that the computation fails to produce a value of type A. And also they have to supply another function, which I'm calling f here, could be called if present, which will be called if the computation succeeded to produce an A. And in the end, interpret is going to return a Z. This function is polymorphic in Z, so it ends up getting its Z either from if absent, if there was no A inside that maybe, or it gets it from F if there was an A inside that maybe. So it's going to get it from one of those 2 places and end up returning that Z. How it does this is it matches against the maybe data type. If the A is present, it calls f of A to immediately return the Z. If it's absent, then it just returns the if absent value to return the default. If the case is map, then it interprets the thing that's being mapped and then composes the mapper function together with the f function and passes along the if absent default value. And then finally, in the case of chain, it's another relatively straightforward recursion that just passes things along, drills down into the inner data structure, and then maps the output by the f function. So you can follow the types here if you want to do this. The compiler will help you write this function. You don't have to think about the implications. Just try to get the types right, and you'll end up with something that's correct. So this interprets the 4 cases. And notice how this is much more complex than the option type built into Scala. Why? The option type built into Scala only has 2 cases. And that's because the option type built into Scala does just-in-time interpretation of the instructions map and flat map. Rather than building up a full description of the effect, what happens is it takes shortcuts. The map and flat map on option will look at that data type, and if it's none, for example, it will immediately return none. If it's sum, it will immediately deconstruct that sum, apply your mapper function to it, and return a new sum. So in essence, what's happening is the option data type in Scala, even though it's a functional effect, it's doing a type of just-in-time interpretation. It's taking shortcuts and returning you a maximally reduced data structure right away, which is why it can afford to be a whole lot simpler than the version I've shown before. But keep in mind that's a simplification, and in many types of real-world functional effects, you can't make that simplification. You need to store every single instruction that you want to expose to the end user of your API. Every operation, every common operation in a functional effect system has a corresponding type class in functional programming. You don't need to know this, but it is helpful to know this. If you've ever used type classes from cats or Scala Z, you've run into applicative and functor and monad and apply and monad plus and lots of other type classes. It turns out that every single type class gives you an operation that you can use in your functional effect. More powerful functional effects have more operations. And the set of all operations given to you by your functional effect type determine how powerful it is and what types of things you can do with it. The pure or point operation from applicative gives you the ability to take an A and lift it up into your functional effect system. It's the equivalent of returning a value inside your functional effect. It's the sum constructor in option. It's the list singleton constructor in list. It's the future.successful in future, and so forth. Empty or zero, some types have this notion of an empty or failure type. Other types have the ability to map over them. Nearly all functional effects, actually all functional effects, almost all, have the ability to map over their contents, which corresponds to taking that return and return statement and changing it into a value of another type, turning an option of an int into an option of a string by converting the int to a string. Flat map is a very powerful capability allowing you to chain two functional effects together in sequence such that the second functional effect depends on the runtime value produced by the first. When you call flat map, you supply the first functional effect, and then you also specify a callback. And that callback will be called with the value of the first functional effect, assuming there ever is produced one. Of course, some functional effects, like option, can fail, in which case they'll never call your callback. But also some functional effects, like future, for example, can succeed at some point in the future, in which case your callback will be called, and you'll get a chance to return the rest of your computation. And the flat map operation is responsible for fusing those two things together, the old functional effect and its chained successor, into a single functional effect. And then finally, zip, otherwise known as app, is capable of taking two functional effects, FA and FB, and zipping them together to get an F of a tuple of A and B. And that's it's not as powerful as flat map, but it's still a very powerful operation. And it's the minimum needed to have compositional semantics on your functional effect. You need to zip two options together, zip two parsers together, to zip two futures together. You need the ability to operate, take two different effects and combine them together into a single effect to solve most classes of problems. Nearly all functional effects in existence support the pure or point operations, the map operation, and the zip. If you don't support zip, if you just support pure and map, it's not that useful of a functional effect. So most all of your functional effects out there are going to at least support zip. And some extremely powerful ones support monad, which gives you flat map, which allows you to do two operations in sequence such that the second one depends on the runtime value produced by the first one. A lot of functional effects turn out to support flat map. A lot. Parsers, futures, options, lists, all kinds of functional effects support this capability. Even the alarm one that I showed you supports this capability. And that's because a lot of the real world is sequential. You do one thing and then you do something later, and the thing that you do later depends on what you did before, depends on the result of what you did before. That is a sequential flow. It's the most complex kind of sequential flow because it's context sensitive. You can change your mind and do different things based on what happened before. That's flat map. That's monadic. As a result, Scala actually has special syntax for data types that support flat map and map. And this is the for comprehension syntax. And it reads very procedurally. You're going to look up a user, and then you're going to get their profile, and then you're going to get your picture URL, and you can imagine all these things returning option. And Scala will desugar this into a bunch of flat maps followed by a final map, allowing you to use functional effects that support sequentiality in a way whose visual appearance resembles that sequential flow of operations with the scoping rules you would expect. That is to say, inside this hunk in the for comprehension on the left, I have access in the line that says pick, I have access to both profile and user. I have access to both of those variables in that scope. In the line that says profile, I have access to user. And in the yield statement, I have access to all three variables, which is the way you would expect scoping to work if these were statements. So every functional effect is an immutable data type, together with the operations it provides for addressing some business concern. And at the end of the day, every functional effect system, we need to be able to interpret it into something else that gives it meaning. This interpretation is fold on option. It is unsafe run on task. But there's always an interpretation function for all of these. It's run on the state monad. It allows us to take this model that describes our business concern and translate it into something that we can use. Let's take a brief look at some of the effects out there in the wild, some of which you've already seen because they're built into Scala, but a couple of which may be new for you. First, the effect of optionality. Either something is there or it's not. The core operations of option are the sum and none constructors and map and flat map. And then its execution and interpretation is the fold function on option. We specify what to do, what to return if it wasn't there, and what to return if it was there. And we can use it in for comprehensions like I showed before. The functional effect of failure is used when we have computations that may fail with a specific type of value. Either has two different instructions, a left and a right. Left is used to indicate failure, and right is used to indicate success. Its core operations are constructing a left and a right, mapping and flat mapping, and then to execute or interpret an either, we fold over it, specifying what to do in the left-hand case and what to do in the right-hand case. And because it supports map and flat map, we can use it in for comprehensions, in which case we're flat mapping over the success case. So if there's a left case, if one of these methods like decode profile returns left, that short circuits the entire computation. We achieve the short-circuiting behavior of exception handling without actually having exceptions in our code. The writer functional effect is less familiar. You may not have seen this before. Writer is actually dual to either, only in this case I'm using a very specialized variant of writer that happens to be the most common. Writer is basically a tuple. On the left-hand side, it accumulates a vector of some type W. That's your log. So writer allows you to log stuff, like log strings or whatever, and those get accumulated in the left-hand side of the tuple. And every writer effect can also produce a value of type A. So the writer functional effect, it cannot fail, it can just succeed. And it can accumulate a log as you're succeeding with values of different type. The core operations for this one are pure, which allows you to take an A value and lift it up into the writer effect. Right, which allows you to add to that log. And then map and flat map like we've seen before. And then how you run that is you just pull out the tuple of the vector and then your success value. That gives you the log and then the value that the writer data type succeeded with. Because it has map and flat map like the other ones, you can use this inside for comprehensions. And you can interleave, for example, success values with log statements, and you end up accumulating those log statements, in this case strings, inside the vector that you get when you run that functional effect. State is another very common functional effect that allows you to model stateful computations. And the state functional effect is basically a function. It's, at least this is the short-circuited version. We could do the full-on different instruction version that I did for optionality, but we were only going to do that once. Here we're taking a shortcut and we're defining it as a function that takes the old state and returns the new state and a value of type A. So state cannot fail. State can always change the state. When you call run, it can change the state, and it's always going to succeed with a value of type A. The core operations are to take an A value and to succeed with that value without changing the state, to get the state and to set the state, and then of course map and flat map, like we've seen with all these other functional effects. To run a state, we have to supply the initial state, as well as the state type, and then out of that, we get back the new state and the success value. Because this functional effect, like the other one, supports map and flat map, it means that we can use it in 4 comprehensions. And we can write code that looks like this, like it's actually incrementing stuff. It's setting a value to be 0, it's getting it, it's setting it to be 0 plus 1, and then it's getting it again. And if you actually run that functional effect, then you're going to end up with 1 out of that, which is what you would expect. It looks like procedural code, but it's in fact not. It's purely functional and it's operating on immutable data. Another less common type is the reader effect. And the reader functional effect allows us to thread access to some environment of type R throughout our program without having to do any of that plumbing. And we can access that R at any point we want. So it's there, always in the background. It's like the context. It's the environment in which our program runs. And we can pull it out, basically pull it out of thin air anytime we want. But we don't have to deal with it unless we want to. And it can be defined by a simple function from R to A. The core operations are pure, like we've seen before, a way to take an A and lift it up into a functional effect, a reader functional effect. Environment, which basically allows us to pull that R into the success value of the reader, and then map and flat map. And then to execute or interpret this functional effect, we have to give it an R. That's the R required by the reader, and then it can give us back the A. Because it supports map and flat map, we can use this in 4 comprehensions. In this case, I just pull the config out of the environment, and I separately pull out the port and the server and the retries, and I yield the tuple of the results. And finally, the last functional effect that we'll look at is the effect of asynchronous input and output. And you can define your own very simple type for async IO by creating a case class with that unsafe run signature. The unsafe run, you give it a callback and it will call it at some point in the future. This is the essence of asynchronous IO. And the core operations are sync for synchronous IO, async for async IO, fail if you want to fail this thing, and then map and flat map. And then unsafe run, you have to give it the IO that you want to run, and then you give it a callback, and it will call your callback at some point later with either a success or a failure. So what did all these things have in common? They're all immutable data structures, every single one of them. They were all equipped with operations that allow us to compose these things together. Nearly all of them supported, actually all of them supported pure and map and flat map, which allow us to build up and compose sequential things together, which is very, very common when you're dealing with functional effects. And then all of them, without exception, had some way to interpret or execute them. These are the building blocks of functional effects. Functional effects are always, always, always immutable data types that declaratively describe a bunch of different operations in some business domain that you can end up interpreting to translate into something that's lower level than that specific concern. Like we can translate away from optionality by providing a default value. We can translate away from error handling by unifying the left and rights of either, and so on and so forth. They all allow us to escape that concern and move it into something that's lower level, which is a key property of building programs compositionally and modularly. Unfortunately, the functional effects that I've shown you are not that useful. They're fun to see one time in your life, but they're not that useful. And the reason for that is, how often is it that you need to be able to fail, but you don't need to do any I/O? Or maybe, how often is it that you need to be able to read from some environment, but don't need error handling or state or anything else? How often is it that you only need to be able to log as you're going along and don't need anything else? Basically, real-world problems, real-world programs, they don't use these toy data types. And that's because they need multiple effects at the same time. A lot of our programs need the ability to fail and to do async I/O. It'd certainly be nice if they could be stateful along the way and update and get state. And it would be nice if they'd have access to like config information or other sorts of environmental information. And that requires combination of 4 different effects, and those data types that I showed you can't support that. So the question arises, let's say we want 2 of these effects. We want optionality and we want error handling. What are we going to do? Well, one idea is, let's just take an option and stick it inside the success case of an either. Let's try that and see where it leads. If you do this, it turns out, I define this my own ad hoc option either data type for what is essentially an option stuck inside of an either. It has, you can define map and flat map such that they work on the A inside the option, inside the right-hand side of the either. So if there's something inside, if that either is a right, so it's a success, and if that option inside the right-hand side is a sum, then the map and flat map will allow you to operate on that success inside a success value. You can also define pure, and of course you can define lift, which is just taking an option and lifting it up into the right-hand side of the either. Unfortunately, that's only useful, and by the way, this is useful if you want the effect of both optionality and error handling. You can use this, and it works. And many people, even though they've never defined anything like this, I've seen in many different code bases, people have defined something like future option, or future either, or some combination of future and something else. I've seen that in code bases, and it's hand-coded like this. So you can take this general idea and you can abstract over it. And how you do that is by introducing higher-kinded parametric polymorphism. You forget the fact that this is an either. We want to say, we want to stick the option in something, but we don't want to know that it's an either. We want to forget the fact that it's an either. And to do that, we use a higher-kinded parametric polymorphic type called F here. It has the shape of things like option and future and so forth. And you can use it for either if you partially apply the either for its first type parameter. Anyway, all the either E stuff goes away. So anywhere you saw an either E in this preceding code block, it has now been replaced by a generic F square bracket something square bracket. This is the next step. And this thing has a name. It's called OptionT. And this general class of effects stuffed inside of effects is called monad transformer. This is the OptionT monad transformer. They're called monad transformers because if you stick a monad inside them. For example, if you stick either inside this OptionT transformer, then you get back a monad. So they take one monad and they transform it into another monad. And you can do this, well, first off, one of the cool things that you can do this for all of the preceding effects that we looked at, except for I/O. There's no such thing as an I/O transformer. And the reason for that is quite technical. I'll omit it. But you can do that for state, you can do that for reader, you can do that for either, you can do that for option, you can do that for writer, you can do that for all the functional effects that we looked at, and many more beside. And all these monad transformers, you stick a monad inside them, and you get a monad out of them. One of the cool things that monad transformers allow is local effect introduction and elimination. What I mean by this is if we're working in generic code that works with any monad f, we can temporarily introduce state by stacking the monad or the state t transformer on top of f. And then we can use that state effect in our generic code, and then later on when we're done with it, we can run that state by giving it the initial state, and that allows us to escape from state. And now when we end up returning, we just return an f out of this function. So other code that called into our code doesn't need to know that we use state, because we can hide that. We can hide our use of state. We can keep our use of the state effect local. No one can see that. And this is called local introduction and elimination. We locally introduce state, and then we also, in that same scope, we eliminated it. That is very, very powerful. In fact, as simple as this seems, it's almost the defining characteristic of monad transformers. They allow modular composition of separate effect types, such as state, writer, reader, error, option, so forth, into a single functional effect with the ability to locally introduce and eliminate effect types, at least the effect types that you know about. All right, so what happens if we need more than one? Obviously, we can stick OptionT on top of either, and that gets us the bundle of option and either. But what happens if we need option and either, and writer, and state, and reader? Well, fortunately, monad transformers are very composable. All we have to do is keep stacking these things. And we can stack them all day long. This is OptionT on top of EItherT, on top of WriterT, on top of statT, on top of reader. So we have all the effects in one God monad. That's not very pretty to look at, but we can deal with it. The real drawbacks are that it's not very pleasant to use a deeply nested stack of monad transformers. It's very painful because every time we want to construct a value somewhere inside that stack, we've got to do a lot of wrapping to get it up to the right level. Now, in fairness, tagless-final can eliminate some of this pain. Tagless-final is not an alternative to monad transformers, and it's not an alternative to effect rotation. Tagless-final can be used with effect rotation or with monad transformers. In either case, it adds a layer of indirection that helps you eliminate some pain and also helps you just abstract. But the drawback of using tagless-final is that we lose information on the concrete structure of these data types, and that interferes with our ability to eliminate these effects dynamically. If we're interacting with this stack through a generic F that satisfies a bunch of type class constraints, we've lost our ability to eliminate these different effects. In this form here, we have the ability to eliminate the effects that we no longer need. We can eliminate some and keep the others around, and very, very powerful. Monad transformers also have terrible performance And the reason for that is there's massive amount of nesting that happens. We're taking our data structures and we're nesting them inside data structures, and we're nesting those inside other data structures. And not just that, but all the map and flat map methods that we call, those allocate additional closures. And not only do they allocate additional closures, but they add additional levels of indirection. A map will call a map, will call a map, will call a map. Four map functions being called to map over something a single time, if it happens to be wrapped in 3 layers of monad transformers. And these are all calls to function apply methods, which is basically the worst type of call that you can get, because there's a billion implementations of Scala's function 0, function 1, function 2, function 3. So the JVM doesn't know which one is going to be hit when it's doing that invoke virtual. So probably that's going to be a lot slower than calling a concrete method on a known data type that happens to be final. So we're adding a lot of overhead. And if we're using tagless-final to eliminate some of the pain of dealing with monad transformers, then the overhead goes up even more, especially at a point where your instances for your type classes are defined on a single monad transformer layer. Because then potentially, for example, if you're using Cat's effect and you stack a bunch of monad transformer layers, then your derivation of that type class for all the Cat's effects type classes is going to go through multiple hops, basically. It's going to end up going through those same Cat's effect type classes one time for every layer of your monad transformer stack. It's piecemeal derivation versus just building up a whole stack of monad transformers and writing that instance yourself. And every sort of roundabout through those type classes is going to add indirection that cannot be optimized around. The JVM's not smart enough to do that. It's best to use a concrete stack, but you're not going to do that in practice because you're not going to derive all these instances for all possible monad transformer stacks. So you're going to rely on the auto derivation, which is going to go through the instances at every layer of the transformer stack. Another fairly serious drawback, at least is, in my opinion, is that monad transformers are order sensitive. That is, if you stack state T on EItherT, that's not the same as stacking EItherT on state T. Those are totally different. And so if you have an n-way stack of transformers, there are a lot of possible ways you can rearrange them. Way too many. And they have totally different effects in your code. And most of them are terrible. Most of these combinations are not fun. Can anyone tell me which of these two you want? In general. No? One of these you want, in general. The other one you almost never want. I would say never, but maybe some people would say they want it, just to prove me wrong. So, choosing that order, I mean, obviously, the more you practice, the better experience you get. But in my opinion, this is too many dimensions of variation, especially considering the fact that in most cases, there's one really sensible ordering that does what most people want. And when you want the other fringe use cases, there are ways to work around whatever ordering you've chosen. And then the last one I already briefly mentioned, which is tagless-final can eliminate some of the pain. First, tagless-final is not an alternative to monad transformers or effect rotation. It is a layer of lipstick on top of either. And you can use, obviously, it with either approach, but the problem is when you use tagless-final with monad transformers, then you lose the ability to do local effect introduction and elimination, because your knowledge about the concrete structure of these types goes away. And with it, your ability to peel off a layer or multiple layers of that monad transformer stack, that goes away as well. Whereas, at least if you use tagless-final with effect rotation, then you preserve the ability. You have to use a different formulation of tagless-final than the common F_1, but if you use tagless-final with effect rotation, you preserve the ability to eliminate effects. And finally, as you might suspect from type signatures this hideous, due to this encoding and limitations in the compiler, if you use monad transformers, you will be specifying a lot of types manually. It's gotten better than it was in the old days, but there's still many cases where you are going to be manually specifying types. And these types are not simple to specify because you have to partially apply them. You can't fully apply them, you have to partially apply them. And that means if you want to get it this pretty looking, you have to use a compiler plugin called Kind Projector, which allows you to use the question mark character. You don't even want to see the version without Kind Projector, because you would probably run away from Scala and never write a line in your life. You use anonymous structural types and type lambdas, type projection, and all kinds of crazy stuff. You would not want to see the desugared form of that. Fortunately, Scala 3 is getting first-class support for the feature that Kind Projector enables. So this is basically the upper bound of the kind of complexity that you'll have to deal with going forward. So let's take stock of monad transformers. First off, they do allow us to combine effects. We can create something that has the effect of optionality and failure and a reading from some sort of environment and a writing to some kind of log and so on and so forth. We can create a type from that in a modular fashion by snapping together pre-built bits of functionality that neither you nor I wrote. And that's powerful. Also, importantly, monad transformers allow us to do local introduction and elimination of effects. We can introduce state and then eliminate it, which means we can hide implementation of one part of our code from other parts of the code. Type inference isn't so good. The order sensitivity problem is there, and you have to live with that. I don't know why intro elimination is listed twice, but I'll blame the jet lag, 9 hours, 10 hours time zone difference. Monad transformers are encapsulated. And what I mean by that is the state T monad transformer does not know about the option T monad transformer. Those effects are different. One does not know about the other. The implementation for the functionality of option T and state T is totally independent. There's no knowledge sharing. That encapsulation is good. It is in general a good property to have. And ergonomics are not that great. You haven't seen any realistic code with this, but if you look at monad transformer code that's not using tagless-final, it is not ergonomic. It is very painful. All right, so let's take a look at effect rotation and see if it can help us gain some of the benefits of monad transformers without the costs. The simplest possible example of effect rotation, actually it's so simple you can't even call it effect rotation, but it'll get the point across, is the either data type. The either data type can be regarded as a data type that combines the effect of the identity functional effect. This has been called the identity monad. The identity monad is a data type that holds a value of some type A. It always holds one value of type A. It only supports success. It doesn't have a notion of failure. But the either data type can be regarded as the composition of the identity effect with an error effect, thus supporting both success and failure. And the interesting thing about the either data type is it supports effect introduction and elimination. Given a value of type E, we can create an either such that it will fail with that E. But it also supports elimination in the following sense: given an either and a way to turn that E into an A, we can remove the E from the type signature and replace it with nothing, indicating that we've eliminated the potential for that effect to fail. That either nothing A, we know that's a right of an A. We know that's a right of an A because there are no values of type nothing. There are no values of type nothing, so there's no way to construct a left of a nothing. So we know for a fact that either of nothing A is in fact a right of an A. So using these two functions, fail to introduce errors and catch all to eliminate them, we can see some similarity to the monad transformer EItherT. Monad transformer EItherT, we add EItherT on top of something if we want to introduce the possibility of failure, and then we run that by specifying a way to handle the error to eliminate that possibility. And here you're seeing something that's similar. You have to squint, but there's similarity here. We're introducing dynamically, we're introducing and eliminating an error type, and we have compile time proof of this introduction and elimination by looking at the types. This turns out to be the key for effect rotation. Why stop with error effects? Instead of nesting our effects vertically, that is to say, have an OptionT, have an EItherT, have a stateful, have a ReaderT, and so forth, we'll just create one type parameter for every effect. We'll go horizontally. So different effects will correspond to different type parameters. And then a change in that type will allow us to introduce or eliminate an effect modeled by that type parameter slot. So in EIther, we have a model of reader plus error plus success. So this is effect rotated version of ReaderT stacked on top of EItherT stacked on top of identity monad. And what it is it's just a function from R to either an E or an A. And we can in fact introduce and eliminate this R parameter. Introduction occurs through this function which I've called environment that gives us access to an R, any R of our choice. Obviously, some choices will limit our composition, but we can obtain access to that by pulling it into the right-hand side of the success channel in this data type. And elimination allows us to, given an EIther, we can feed it an R, and that's going to turn the R requirement from R to any. And any here means that this EIther does not require any specific value. In other words, in order to run this, we could give it unit or the number 42 or an empty string or whatever. We've eliminated its dependency on any specific type of environment. So this shows us that using this data type with 3 type parameters, we can dynamically introduce and eliminate both errors, the E type, the error type, as well as environment type. Whenever we eliminate the error type here, it goes to any. When we eliminate the error type, it goes to nothing. Note that this naive encoding actually shares some performance overhead with monad transformers. It's way better than monad transformers, way better than monad transformers, but there still is some overhead. And the overhead comes from the following function, or following fact. Let's say we have a segment of our code that's not using the environment R, and it's only succeeding. It's not failing. In that case, every operation we do, every flat map on this data type will involve constructing a lambda that ignores its R parameter, and then takes its success value and wraps it in the right-hand side of an either. That's overhead, and that can be measured in performance benchmarks. And on every single flat map, we have that overhead on the happy path. The happy path is no use of R and success. Failure we don't have to worry about, that's not on the happy path, it happens very rarely. Use of R, not on the happy path. So we have to worry about this only in the happy path. This has substantial overhead for even though it's probably an order of magnitude less than the corresponding monad transformer version, it still is concerning. We have the dispatch overhead of all these additional lambdas that we've got to go through, and then we have the boxing overhead of the either in the success case. And yeah, we have a few type parameters here, and that's only going to get worse once we add more effects. So this is effect rotation taken to its logical conclusion. This is the God monad. And it's horrible, right? We have reader, writer, state, error, and success. That's a lot of type parameters. It's a mouthful and it's unpronounceable. But even with this God monad, it turns out to be possible to eliminate happy path overhead. And I'm not talking about reducing it like that run function in the ReaderT data type. I'm talking about eliminating it. And how we do that is we build our own free monad-like construction. And then we implement an optimized run function, which, given the R required by the reader and the state, the S required by the state, is capable of producing us the log, the new state, and either an E or an A. This run function is like the God run function. You have to give it everything and you get everything. But we can build a data type here with all these different cases. That is, we can build success, we can build a reader and a run reader, error, state, writer, and run writer, and then we build a flat map, and that's all it takes. We build all this stuff, which admittedly is painful. It's painful, it's nasty to look at. And then we can implement a hyper-optimized run function that will not do any additional allocations or boxing for the happy path. In other words, we can get the benefit of that 5-way monad transformer stack, but without any of the overhead, and still with the ability to dynamically introduce and eliminate these different effects. And the structure of this is very regular. There's principles going on behind here that you may not see. Elimination laws. So there's a very regular set of rules that you can follow when introducing the operations for elimination. If you're dealing with a covariant effect type like failure or optionality or writer, then its elimination will take that type parameter and transform it to nothing. Of course, you're going to have to force the user to deal with that value, to move it into value space or something. For example, if it's an error, they have to recover from that error. They have to do something. In the process of eliminating that effect, the user has to do something. For a covariant functional effect, they have to handle it. So you can change that type parameter slot into nothing. That information has to go somewhere, like into the value channel. For a contravariant functional effect, like reader, don't worry about those words. If you've never heard them, don't worry about what they mean. Covariant just means you get it out, like you get out an error from an effect. Contravariant means you put it in. Like to run a reader effect, you have to give it the environment that it requires. That's what contravariant means. So for contravariant, you're going to have to eliminate it, you're going to have to give it what it needs, and then you're going to end up with any in that type parameter slot, indicating it doesn't need anything anymore. And then finally, for an invariant effect, like state, for example, state, you have to give it the old state, and then you get out the new state. So for state, you have to feed it an S, and you get an S out. So it's not covariant or contravariant. It's not covariant because you have to put something in. It's not contravariant because you get something out. It's invariant. And for that, you eliminate it by, well, requiring that they put something in, and you can always ignore the thing that comes out if it's not necessary. And then you end up eliminating that type slot by changing it to unit. An example would be state. All right, so let's compare monad transformers to effect rotation. First off, both can do intro and elimination. That doesn't change. Neither does the repetition of intro or elimination, which I apologize for. Type inference, effect rotated types can be inferred fully. If you annotate them correctly with type parameters, they can be fully inferred by Scala. In all cases, no type annotations required. If you don't know what types to type, just have your IDE insert the types for you. Effect rotated types are also order insensitive. That's because in the interpreter that you build for these things, you make a choice of what meaning to ascribe the composition of the set of effects that you're dealing with. And you can choose the common meaning that most people would choose when building the monad transformer stack. Effect rotated types are also very ergonomic. So despite the fact that they have more type parameters, they infer fully, and they're lower kinded type parameters. There's no higher kinded F stuff. So people using them don't need to know higher kinded types, and they never need to supply any type annotation. Their IDE can always insert types wherever necessary. The compiler will give very good error messages when these things are necessary, and there's never a need to chain anything. You just directly call, for example, fail or read or all these different methods. You directly call them on the data type, so your IDE helps you with discoverability. I would say they're 10 times easier to use than monad transformers, just in terms of being able to sit someone down and have them be productive 30 minutes later instead of 3 days or 3 weeks later. Unfortunately, it's not perfect. There are trade-offs to everything, and effect rotated types fail at encapsulation. So remember, the OptionT implementation adds optionality and doesn't know anything about the EItherT. Those are independent bits of code. They're modularly separated, and they can be combined together to give us the combined effects of those two functional effects. That's not true for effect rotation. In effect rotation, we determine the set of effects that we are going to support in advance, and then we write a single low-level optimized interpreter that knows about all those effects and weaves them into the data type. So there's no encapsulation with effect rotation. And in a sense, you can view this as a lack of orthogonality. In an ideal world, every effect would be completely orthogonal to every others. They would be totally isolated. None would know about the existence of others. The implementations would be totally separate, and we would somehow compose them together. And yes, we can achieve that, but we achieve it at extremely great cost in Scala. And even in Haskell, these things have significant overhead, but in Scala, the overhead is even worse. So if there's one thing to sacrifice, then in my opinion, it's encapsulation, because that appeals to my engineer brain. A nicely encapsulated orthogonal solution really does appeal to my engineer brain, but in day-to-day programming, what does it matter? Not that much, because especially if someone else went through the pain of creating the hand-optimized interpreter. So these techniques are applied in the library Zio. And in this section I'm going to step through, we're going to talk about how you can get the benefits of monad transformers. Not just monad transformers, by the way, because if you want this like godlike monad, I have the code for this. I can share it with you. And the nice thing about this God monad is that basically it has everything you could ever want in it, practically speaking, and you can run this thing in a pure way. So it allows you to do all your non-IO effects. If you need a bunch of stuff, you're doing parsing or whatever, and you need error, and you need state, and you need reader, and this and that, you can use them all, basically. And then you can run this and get a pure value out, and you don't have to do any IO. So there's no unsafe run here. This is a safe run. You can call this, and it's a safe run. And then if you don't like all these type parameters, you can always type alias it to ignore the ones that you don't want to use. So we're going to look at a version of effect rotation that, yes, it does combine the common effects that you need in FP, but it also does concurrency and async programming, which is the big thing. Like, that is the big thing. In modern applications, your modern app will be async and concurrent. That is guaranteed. And so that is the workhorse on which the other effects are layered. So Zio is primarily about async and concurrent programming, but if you happen to be doing async and concurrent programming and need something else, well, Zio probably has a way for you to do it without using monad transformers. So interestingly, Zio has only 3 type parameters. Only 3, I say. That's more than many would like to see. It has reader for the reader effect, error, and then the success type parameter. So 3 different type parameters. You can interpret this as being a Zio effect requires environment R, so it needs you to give it an R. You can't run an effect without giving it the R that it needs. Now obviously if that R is any, you can give it anything you want to run it. But in many common cases it's not going to be R, it's going to be something else. And this is how you achieve testability and pass config around your program, or an HTTP context or something else. It's how you propagate information throughout your program without having to do the manual plumbing and wiring necessary to do that. The error effect, of course, is, you're familiar with that. In many cases this might be throwable, or exception, or IO exception, or maybe you have some sort of data type for application errors. You can plug that in there. And in some cases it will be nothing. If you catch all errors, E turns into nothing. You've eliminated that effect, and the resulting effect can no longer fail. And then the success type, that's the same as the type parameter in future, or in Monix task, or in cat's IO. To support the effect of reading, you have provide, which is the way you eliminate the R effect. You give an effect in R, and suddenly that type parameter goes to any. It's gone. It doesn't need anything now. Doesn't need anything in particular. Environment is how you access the environment. And then access-m provides a very common way of looking at that R and then doing something based on it. Access-m is actually the more common way to use the environment, although you can implement one in terms of the other, so you only need one of those. You need 2. That's the pattern of functional effects, by the way. You need introduction and elimination. You're going to see at least those in all your functional effects. Error, you have the way to take that error channel and eliminate it. That's either, at least that's one of the ways to do it. That shifts it over into the value channel, into the success channel. So now your success channel has an either E or A. That's in your success channel. So the error disappeared. It popped on over, it skipped on over to the success channel. Now it's gone from the error channel. That resulting effect can't fail, but of course you're going to have to deal with the fact that the value in there might be a left of the error. That's effect elimination. So one way to do effect elimination. And then you have introduction with fail. You give it an E and you get back that E stuffed in the error channel. And then of course you have introduction for success as well, which is called succeed. All right, so how do we do the effect of optionality using Zio? Well, option turns out to be isomorphic to either unit A. Option of A is the same information content-wise as either unit A, because you map the none to left of unit, or you can map the left of unit to none. Remember, either succeeds with the right of an A or fails with a left of an E. So if your E type is unit, then you can go both ways. You can map none to left of unit, you can map left of unit to none, and then you map sum to right, sum of A to right of A, and right of A to sum of A. So you can go both ways without losing information, which means those 2 data types are isomorphic, which means you don't lose any information in the translation. It's invertible. So this is exactly optionality. So if you're not using errors and you just need optionality, then that's how you do it. What happens if you need optionality and errors? That happens sometimes. Like for example, in defining HTTP routes, it's possible one route handler just didn't handle that route, wrong path. That's not an error. But it's also possible that route handler decided, yes, I'm going to handle this. And then it failed midway down in issuing a response or querying a database or doing this or that. Sometimes you need both optionality and error handling. So how do you do that? Well, you model that entirely on the error channel by using an option of an E. And there are combinators on ZOFX to make working with this very natural. So you actually don't need monad transformers. You can combine this. And this works for any number of levels that you can imagine. All right, so that handles, obviously we have reader baked in. We have error baked in. We can do optionality just by using unit for the error channel. And we can even combine error and optionality by using OptionT. What about the other combinations? Well, the obvious ones that we're missing are state and writer. Amongst the pool of common functional effects, we're missing both state and writer. How do we do that without adding yet more parameters to ZIO, which we don't want to do? The key to unlocking the other effects is a data type called ref. So ref is a model for a mutable cell. And ref is equipped with atomic update and modify operations as well as get and set. So you can think of it as the functional version, the purely functional version of a var. Only it's better than a var because no operation on a var is atomic. If you have some var that's an integer and you do I plus equal 1, that is not atomic. That's translated into many bytecode operations that can be interspersed with other operations from other threads. So you're actually going to lose information if you treat that as an atomic primitive. Whereas these update and modify operations truly are atomic. So it's a better version of var. It's a concurrent safe version of var. And once you have a ref, it turns out that implementing writer is trivial. All you do is use your reader effect to plumb access to your log stored inside a ref. So you have a log which is stored inside a ref. It's a vector of W stored inside a ref. And then you plumb that around using your reader effect. And then you just need a single write operation that, given a W, will go ahead and append that to the log by accessing that ref through the environment. And once you pull that trick with writer, it becomes very intuitive to pull it with state as well. You simply store the state inside a ref. And now you can write modify, update, and get state methods that access that ref through the environment. So you don't have to plumb that ref around. You don't have to pass that ref around manually. It'll always be accessed through the environment. And this trick, by the way, I was not the first to recognize this. I read an article by Michael Snoyman, written quite some time ago, who successfully applied the technique in Haskell first. So if you want more information, and I don't know if he came up with it or if it was around before him, but he certainly saw it and I think was among the first to write about it. But Google the ReaderT design pattern if you want to know more on the history of this thing. Basically, reader is the most powerful effect of all in some sense when you're working in the I/O monad, because its presence allows you to implement other functional effects such as writer and state and many other types. So what does this mean? It means that 3 type parameters are actually all you need. I/O is sufficiently powerful enough that 3 type parameters are all you need to reconstruct that dreaded God monad, should you need it. The God monad can be defined, at least a next generation version of that God monad could be defined simply by requiring that our environment have both state and writer. So our environment needs to have both those refs, one ref for state and one ref for writer. And then we'll go ahead and layer optionality onto error by sticking the error in an option. The important part of this is this here. Notice how we're using a ZIO effect here. This is just a type alias, but this ZIO effect here has R and then E and then A, just like always. Using those 3 type parameters, we can have error, we can have writer, we can have state, and we can have, obviously, success, and we can use that R to carry around lots of other things. If we want to do testable effects via the environment, or have other functional effects that require state, or config information, or context information, or whatever, we can use other parts of that. Ooh. We can use, there's lots more room in that R. We can stick whatever we want in there. And interestingly, not only have we built something that is as powerful as that massive stack of monad transformers, and not only is it, because it's powered by effect rotation and not vertical stacking, it's powered by one type parameter for every different effect, plus we were able to recognize the fact we didn't need new type parameters for state and writer. Thank you. So not only is it more performant, it's way more ergonomic. Everything infers fully. We still have the ability to locally introduce and eliminate effects. It's as performant as zero monad transformers, just sort of raw effects, a raw functional effect. It can be as fast as that. Not only have we gained the ability to model this God monad put together by the 5-layer stack of monad transformers, along with all these other benefits, but in modeling state and state and writer using ref threaded in the environment, remember ref is concurrence safe. So that log that's stored inside a ref and that state which is stored inside a ref, suddenly all our updates to state and the log become concurrence safe. In other words, our concurrent application, we can have lots of different fibers in our application all updating the log, and that's totally fine. We can have lots of different parts of our application, lots of different fibers updating state concurrently, and it's guaranteed to happen in a synchronized and consistent fashion. So we get concurrent safe state and concurrent safe writer, and then because the base monad is resource safe, we also get resource safe state and resource safe writer. This is another problem I didn't go into depth, but when you use monad transformers, you lose resource safety. So if you want to acquire something and then release it, you have to forego that ability. You can acquire something and you can possibly release it, but you can't guarantee to release it when you start using monad transformers. We have resource safety here in addition to concurrency safety. And we paid a price to get here. There's no free lunch. The price we paid is non-orthogonality, lack of encapsulation. We have a single effect type that has knowledge about reader and error and success and manages all that internally. And those are not independent. They cannot be layered on independently. But it turns out that those 3 different effect types are sufficient to implement all standard effects in the monad transformers sphere. MTL effects, they're called. So using just those 3, we're able to recapture all the benefits of monad transformers across the standard effect types, but in a way more performant, way more ergonomic fashion that's totally type inferred, and also concurrent safe and resource safe. And I'm not a purist. I like to write software that solves the business problem. I'd like to do so in a principled fashion as well, but I will not prefer the most pretty thing possible if I can have something that's equally principled and maybe sacrifices a bit on orthogonality in order to get the other concerns addressed, like ergonomics and performance. And I think that effect rotation, even though it isn't perfect, it hits the sweet spot in Scala. It gives us everything we need in a very high-performant, easy-to-use, pleasant package that may not be theoretically or orthogonal, but for day-to-day programming, most people aren't going to care all that much. All right, well, if you like things like effect rotation and monad transformers and functional effects systems, concurrency, all that good stuff, then I encourage you to follow me on Twitter at jdgoes. I also blog as often as I can, which is not very often, and not as often as I should, but I blog at dgoes.net, so please check that out. Any questions? Yes?
The slide 73, there was the optionality. You try to express, it can be either error or result with some or none. And there was the error wrapped in option that kind of surprised me, because for me the most intuitive would be to wrap the result into the option, the A.
Right. So the question is, I modeled, so when we're combining error and optionality on slide 73 apparently, good memory, when we're combining error and optionality, the way I chose to represent that was put the option on the error type rather than the option on the success type. And there's a reason I did that, because if you were to build a monad transformer for that, it would assume that nearly every single operation could both not be there and also potentially fail, rather than just a one-off operation. So if you just have a one-off operation that may not be there, then by all means put the option on the success type. But if you're emulating the monad transformer case, where you're combining the effect of optionality with the effect of errors, as you would be to defining HTTP routes, because a given route, you want to define it piecemeal, which means every route has the option of saying, I'm designed to handle this, or I'm not designed. That's where your option comes from. And if they say, I'm designed to handle this, then they're given a chance to handle it, and they might err with some error E, in which case the fallback route is not activated. So in that specific case, there's a very good reason for putting the option on the error. It's because your maps and flat maps now operate on the A, not the option of A, which is the same as the monad transformer case, which allows you to drill into the A inside the option, inside the either. So you're drilling down into working on the A. You can always shift back and forth if you want to, but if you're using a lot of that sort of, route defining logic or similar applications, then you want to be working on the A and not the option. And also there's another reason, which is option of E has performance overhead in the sense that you're wrapping an error in a sum type, but you only pay that on a failure, which is rare. So rather than paying it on the success type, every single map and flat map being an option A, it's better to pay it only in failure, because then the cost becomes insignificant and you're back to a super optimized implementation. So that's the reason why I did option A instead of option E on the error channel instead of option A on the success channel. Yeah. Any other questions?
Maybe more. How do you locally introduce state or writer in the presentation? Yeah. Because the only solution I came up with is like to use a tuple for the environment, which is probably not easy to work with, let's say. So is there some better solution?
So the question is, how do you introduce writer or state?
Yeah.
And so you can introduce writer simply by logging something of that type, which will take the type parameter from nothing to that error type. That's how you introduce writer of a type W, is just by writing something. And then of course you can eliminate it by draining everything from the log, allowing you to create an empty vector there, which will have type nothing in the type parameter slot. State is trickier. So that's a good question. And invariant effects are very painful to work with. There's a set of operations you can use, but they're painful because you have to preserve information. And you're right, zipping, for example, is one way to introduce. You can take this state over here, which requires an S, and this one here, which doesn't, and you can zip them together. And then you can do an invariant map on that to eliminate the tuple and the useless unit on one side. And certainly there should be combinators for making that case simpler. But you introduce stuff by zipping it together in one fashion and eliminating the garbage unit on the one side. Any other questions? Yeah.
Seems like you would need other operations for state, for stateful operation that can fail and not update the state. You can express that with state being on a transformer.
Right.
But it was not that because it can only express using your update for
Right. So
right?
exactly. So the question is, or the comment, the legitimate comment is that this type of state cannot fail. So how do we deal with a type of state that can fail? And there's a couple different ways you can handle that, but the way I like the most that's currently in development in Zio is basically a version of ref that is super polymorphic. It can have errors on the consumption, on the setting side and the consumption side, and you can potentially get something different than what you can set. And operations on that ref return new derived refs. And I think it's going to be possible using that to achieve the effect of stacking together state and error, allowing your set operations to fail. As long as you can unify error types between that and the error type of your overall effect, which you can unify them manually using either or something, but you're probably going to be working in a domain where they're unify automatically if you're using throwable for everything, for example. Good question, or good comment. And yeah, this is not, strictly speaking, effect rotation is not as expressive as monad transformer. And you can see that, the most obvious way to see that is remember the order sensitivity of the monad transformer effect. Just by flipping those, you can achieve different meanings. So you can achieve lots of different meanings. Whereas your effect rotation, it has one meaning ascribed to it by the author of the effect rotated data type, and to achieve other meanings, you might have to do something on the side. You might have to use other data types or something. In my experience, most people don't need that, and they want the semantics of order and sensitivity. They're like, pick the thing that makes sense and just make it do what I want it to do. Any other questions or comments? So question was, what was the motivation to create Zio, and how does it compare with reactive streams? So the motivation was, I looked at the effect types in Scala, and I didn't see a compelling reason to use them from the perspective of a non-functional programmer. Because a non-functional programmer, if you look at flat maps and maps and all this stuff, you're just like, why? Why would you ever do this to yourself and your code base? And I couldn't find a good answer to that. And I'm a functional programmer. I like writing pure code because of the reasoning benefits that it gives me and the testability and so forth. But honestly, looking at monadic code at that time, circa 2017 or whatever, there was not a compelling, there was the async stuff, which was okay, that was started to be interesting, but there was so much potential because in Scala, you're basically writing your own language. It's a monadic language, and so you can embed effects into the interpreter of this effect type, and you can do things like interruption and fiber-based concurrency and timeouts and all these other things that no one was doing. And I thought you could do them, and if you did them, this would give a reason for everyone to use this functional effect type. Not just the hardcore devotees who do FP for FP's sake because they like the reasoning properties it gives them, but this would give a reason for the companies out there who were choosing Akka or they're choosing something else. They're not choosing that because of FP, they don't really care about that. They're choosing that because it solves the business problems that they have. And I thought it's possible to give that treatment to functional effect systems, and it's a unique opportunity because if there's one thing that Haskell has shown, it's that functional programming is extraordinarily good at asynchronous and concurrent programming. Extraordinarily good. It's almost impossible to compete with it without building a whole language designed to do that type of computation. And we'll see if that's successful. I will say I think it's more common for companies who are not doing pure FP to be using Zio than it is for people in the functional Scala subset of the Scala community to be using Zio. And this is early days, pre 1.0. I think that trend will just increase over time. Zio is not the equivalent of reactive streams. Zio can be thought of as the fabric on which quite a number of interesting things could be done, including reactive streams. Zio has an implementation of streams, but it also works great with FS2 and works with Monix EItherT and other streaming implementations out there. It interops with interactive streams, the implementation of streams in Zio, but Zio is more foundational than that. Zio gives you the ability to build reactive streams with new types of capabilities that you can't get out of reactive streams. For example, fine-grained interruption, or locking different parts of a stream computation to different thread pools, guaranteed resource safety, all the stuff that you couldn't easily build on top of the layer that Scala gave us, you can build on top of a library like Zio or one of the other functional effect systems. Any other questions? Yes?
There is multiple implementations of Python, for example, Chats.io,
Yeah.
Z.io, we demonstrated today. There's also different implementations of streams, as you mentioned.
Yeah.
There's two streams in Z.io streams as well, and there's Scala's three streams implementation going on. If all are principled and if all are lawful, why do we need different implementations of those, or do you think one of them will supersede the other, or which one at the end do you think we are going to be using?
Yeah, so the question was, there's multiple effect implementations, not just Zio, but there's also Monix and Cats.io, and there's also multiple streams implementations. There's FS2, there's Zio streams, there's Monix EIthherT, there's the older Scala Z streams, which some companies are stuck on. There's Akka streams, and so on and so forth. Now, I think if you restrict your domain to pure FP, then some of the options fall off the table. But you're still left with multiple implementations. In my opinion, there's no compelling reason for so many implementations of this level of infrastructure to exist. If implementations are going to make a different set of trade-offs that make them very compelling for some use cases and not so compelling for others, then that's a reason for something to exist. And on that border, one could consider FS2 as having taken, first off, FS2 is a general purpose poll-based streaming library done in the pure FP style. And it's very principled, it's very orthogonal, it's a very well done library, I really like it. It's very general purpose. They've taken an approach that enables data flow programming. So FS2 is very good at data flow programming. On the other hand, because it is very general purpose, it makes it harder to make certain types of guarantees around, for example, safe interruption and safe resource release. FS2 stream is not designed to solve the same set of problems that FS2 does. It solves a different set of problems, namely, you need to stream files or data over sockets. You have these potentially infinite streams of uniform data, you need to stream them and handle them. It doesn't try to do anything in the reactive style, and it's not as powerful as FS2. But the fact that it made those trade-offs, even though it makes it less good for data flow and reactive style programming and so forth, allows it to more easily make and observe guarantees about resource safety and interruption safety that is going to be much harder for FS2 to make. So maybe there's a legitimate reason for both those things to exist. But at this point, we have Cats.io, we have Monix, and we have Zio. And I regard Monix as the better version of Cats.io. Alex did a lot of work on both. Alex Nettleskew does a lot of things. It gets a lot of small details better, in my opinion, than Cats.io. So I always recommend Monix as opposed to Cats.io if you're in that market. Now, does Zio need to exist together with Monix, together with Cats.io? Who knows? I guess time will tell. I will say that Zio tries to be very, very principled about things. For example, Zio will always run finalizers. It will always release things it acquires. If you lock an effect to a thread pool, it will go to that thread pool, and when it's done, it will always come back. It tries to make very clean design decisions that sometimes were not always important to the authors of, for example, Cat's.io. So it tries to be strictly less surprising and more consistent than the other effect systems. And then on top of that, it does bundle in the reader and error effects, which allow you to solve common cases without overhead, and comes with a few other common data structures that people often use. They don't always need them, but like async queue is very common. STM, software transactional memory, makes it very easy to write concurrent solutions. It's like batteries included, tries to use less FP jargon, emphasizes type inference and good documentation and so forth. So hopefully it will find, I actually think the Zio market is probably basically all the shops that chose Akka 5 or 10 years ago. Zio is looking a lot more attractive, especially since it's already compiling on Scala 2.11, 2.12, 2.13, on Dotty even. It's very forward-looking to features in Dotty, that it's quite compatible with union, intersection types, the export keyword, trait parameters, all the stuff coming in Scala 3 makes Zio even better at what it does. So I'm very optimistic that eventually it's not necessarily going to be, it's going to be playing in the same space as Akka, but for the Scala user and going forward into the future. Any other questions? All right, thank you so much for attending my talk. I will hang around for a few minutes afterward. Thank you.
So thanks, John, again. Thank you.